Welcome everyone, this is Mrs. Hanson and we're beginning a new chapter in organic chemistry focusing on alcohols, chapter 12. Let me just share with you the selected topics out of the chapter we'll be focusing on. In our first lesson in this recording, we'll focus on section 1, the structure and properties of alcohols, including the nomenclature practice. In the second, we'll review the acidity of alcohols, bringing back some pKa values in comparison to other types of protonated molecules. And finally, in section 3, we'll review the preparation of alcohols via substitution or additions. Quite a bit of review really from chapter 11 with the synthesis chapter. You've been employing many of these same techniques. This allows us to just make a connection with alcohols. In the second lesson, in the next video, we'll talk about preparation of alcohols via reduction. We'll look at the preparation of diols. With diols, we can see that there would be 2 alcohol groups. And finally, we'll look at the preparation of alcohols via a Grignard reagent. That would be the first time we introduce a new reagent for the production of an alcohol. And finally, in section 9 and 10, in the third lesson, we'll look at reductions of alcohols via substitution and elimination, and end the chapter with reactions of alcohols, including oxidation. So these two will kind of go hand in hand. Notice in section 1, or lesson 1, sections 1, 2, 3, then 4, 5, 6, we're eliminating 7, 8, moving directly on to 9 and 10, and then there's an 11 and 12 that we're taking off as well. Title of the chapter is Alcohols and Phenols. We're focusing on alcohols in our lessons. So just make a note of what sections to prepare for and which ones to let go. Let's begin diving right into the structures and properties of alcohols. And we understand that an alcohol is a functional group, the OH hydroxyl group. The ethanol ending, when we hear the OL from the word alcohol, is the technique that we'll practice for the nomenclature as we begin practicing naming and writing out compounds. Alcohols are compounds that possess the hydroxyl group. They can be a straight chain or they can be a cyclic structure. And we'll see that characteristic OL in its ending. Phenols, just so that we're aware, contain a hydroxyl group that's directly attached to the benzene ring. So any one of those carbons from the 6-membered ring, it's a resonance stabilized structure, an aromatic compound, leading out to the OH, we need to recognize as phenol. So we would actually use this as the base name if I were to name a compound such as methylphenol and so forth. So alcohols is the focus of our chapter, looking at OH hydroxyl groups. Let's remind ourselves some of the techniques about naming alcohols. Alcohols, notice the OL ending in the word, are named using the same procedure that we've been practicing all term. Very similar to naming alkanes, but with some minor modifications. We need to identify the parent chain, but very important is that the parent chain must contain the hydroxyl group. So it needs to include the OH. Even if I can find a longer chain, I have to find it with the OH in it. You'll name and identify the substituents. You'll locate them using a number and then alphabetize them. Here's the key. The alcohol gets the lowest number possible. And then just list those substituents in alphabetical order, reminding you that iso is counted in the alphabet, but such a prefix as a di, tri, tetra, or so forth is not included when alphabetizing. And then just name the parent chain as you would an alkane, but changing the ANE to an OL ending. And let's just practice a few to show us that we really do have a good handle on this already, but it's good to review. So the first step said identify the parent chain. If I had a 5-carbon chain, a straight chain of 5 carbon, we can see that it would be a pentane ending. We eliminate the E and change it to OL, and this would be called pentanol for the parent chain. We'd also need to locate where the alcohol group is and tell you in the name that at carbon number 1, we have a hydroxyl group, and the name would end with 1-pentanol. But the emphasis here is to remind us that the suffix ane from the parent chain, that E gets removed and the OL is exchanged to come up with pentanol. Now, in this example, it's emphasizing that the parent chain must include the hydroxyl group. And so if I were to number this particular carbon chain, I can see that there are 8 carbons. However, I also understand that the rule says I must have the hydroxyl group in that parent chain no matter how long the other direction might be, and I have to make it the lowest number possible. So when numbering the carbons in this example, the hydroxyl group carbon number 1 gets priority. The 6th parent chain would be hexanol. At carbon number 2, just kind of following through those examples, we have a propyl group, a 3-carbon chain. At carbon number 1, we have the OL ending, and we put it all together to create 2-propyl, 1-hexanol for that particular example. Even though this chain was longer, we have to number giving the hydroxyl group priority. Assign a locant, which is a number, to each substituent, giving that carbon, the hydroxyl group, the lowest number possible. So just as a reminder, here's an example where we have an ENE, a double bond, and I know in previous chapters that would have received priority and we would have started our numbering system as we're shown in this picture with a double bond between carbon 1 and carbon 2. However, the hydroxyl group gets priority even over a double or a triple bond. So the parent name must start at the lowest possible number for the hydroxyl group and then include the double bond. Don't make it a substituent, but it has to be included in the parent chain. And so here we can see that we end up with a heptene, and that's between carbon 6 and 7. Right? It's kind of just sharing with you what this ends up being. So as we work to find that name, the ENE of the carbon chain is designated with a number. So you could say it in a lot of different ways, really, but 6-ene would give us an idea that we have a, that double bond. Now remember, a moment ago I said if it's a parent chain of an alkane, we did this. We removed the E and turned it to ol. But if we have an ene, we have an enol ending. So we have to let you know where the double bond is in addition to where the hydroxyl group is. So we have to name the parent chain ending in OL and still let you know where the substituent group is. And one of the ways to do that really is to just use the numbering system directly before each of those functional groups. So for example, you'd have 5,5-dimethyl. And then notice here the dimethyl on carbon 5, that's still there just as substituents. You'd have a heptane, so this ENE, so we could say hept, and then you'd number it 6-ene, and then, ENE, and then what you have is a 2-ol. And that lets us know where all of those substituents lie. On carbon number 5, we have 2 groups of a methyl, so you hear that dimethyl. The parent chain of hept has a double bond between carbon 6 and 7, so I hear that as 6-ene. And then at carbon 2 is the hydroxyl functional group, and you hear that as OL. The OH locant is placed either just before the parent name or just before the OL ending, as I modeled above. And it's critical that you put it before the functional group if you have more than one in the parent chain, just as we modeled. So you could say in this example, 3-pentanol or pentane 3-ol. If you had a double bond in there, let's say between carbon 2 and 3, now we must use the locant to let us know that there is both functional groups involved. And we need to number to make sure that not only the hydroxyl group gets the lowest number, but also that the double bond would get the lowest number. So here we'd have a parent chain of a pentene. At carbon number 2, we have the ENE functional group, and at carbon number 3, we would have the OL, the hydroxyl functional group. So we could definitely use the system of putting the number directly before the functional group in this pentene-ol compound. For cyclic alcohols, the hydroxyl group is always carbon 1. So given the priority of carbon 1, and then of course we could number in either direction if there are no other substituents. Carbon number 1 is always assumed, so we don't need to write 1 cyclopentane-ol, that's redundant. You automatically know that the OL is at carbon 1. And even if we have other substituents, the alcohol will be always carbon 1, and then we would begin numbering to give the other substituents the lowest number possible. Carbon number 1 is a chiral center, and so just to recall, we have to indicate if it is spinning clockwise or counterclockwise in its name. Carbon 1 is the only chiral center in that model, and looking at the priority, OH would be priority 1, and it is a dash system. Hydrogen would be the wedge. We don't see it, but we know that it's there, and it would be of lowest priority, which is a 4. And then if we spin from 1, 2, 3, it is spinning it's spinning counterclockwise, but we know to flip that, making it from an S to an R configuration, and we flip that direction because the highest priority is behind the page and the lowest priority hydrogen is coming out at us as a wedge, so we just flip the direction to find an R configuration. And notice, since there's only one chiral carbon, we only need to have one designation, and that would be the R configuration. So at carbon number 3, we have 2 methyl groups and a cyclopentanol. At carbon 1, we've indicated the chirality is an R. We do not put the 1 in the cyclic structure because we already know that it's at the only chiral carbon, and it's always at carbon 1. Here, just another example, we have a hydroxyl group on a straight chain coming off of a phenol. So when we look at this base name coming from the first of our slides, the base name now is phenyl from phenol, and it's being named as a substituent of a 3-carbon chain. At carbon number 1, we have an ol group, the alcohol. The carbon chain is 3 carbons long, so we can hear the base name, the parent chain, being propane-ol, and knowing at carbon 1 we have an OH. Carbon 2 is a chiral center, so this is why I'm seeing the R configuration. The chirality would have it spinning clockwise. And then at carbon 3, we have a phenyl group listed as its substituent. Alrighty, so all just that practice of how to put the names together. They also give us a few common names that we could be familiar with. For example, isopropyl alcohol, the iso group coming because the alcohol group is coming off of carbon 2. This is probably in your medicine chest at home, isopropyl alcohol. Here's tert-butyl alcohol. There's a 4-carbon chain with it coming off of the center carbon. And then benzyl alcohol, which would be phenylmethanol as well. So just some list examples of common names that you might be familiar with, especially from current lab work. Like halides, alcohols are often classified by the type of carbon they're attached to. So in a primary alcohol, the carbon that is attached to the alcohol is attached to just one other carbon. In a secondary alcohol, the alcohol, here being the OH, the carbon that's attached to that is attached to just 2 other carbons. And here we have a tertiary alcohol where the carbon attached to the OH group is attached to 3 other carbons. So very similar to how we recognized primary, secondary, and tertiary halides, we recognize the same pattern in an alcohol. And recall that when an OH is attached to that benzene ring, the parent name becomes phenol. So here, for example, carbon number 1, because the alcohol always gets precedent. At carbon number 2, we have a nitro group, and at carbon number 4, there is a halogen of chlorine. Listing them alphabetically, chloro comes first, nitro would be second, and the base name is phenol. When we have an aromatic ring with a hydroxy group, that's the parent name of phenol. I remembered a moment ago, just to kind of emphasize, when we had a carbon chain, and off of the carbon chain, let's put an OH here, and we could list then as a substituent, a phenyl substituent. Phenol is the alcohol, phenyl is the substituent coming off of carbon number 4. Let's practice. Pause the video and just draw this structure and try giving it a name. You're going to find the parent chain that gives the alcohol the lowest number possible. You're going to identify and number those substituents. I see some chlorines there and a carbon chain. Assemble those in alphabetical order and then try to locate any chiral centers, giving them an R or S designation. And when you're ready, come back to the video and check your work. Well, welcome back, and let's go through those steps together. Give yourself some critical feedback. You've paused. Now it's time to process. Step number 1 said, let's find the parent chain of the alcohol, knowing that it received the lowest number possible. You found a 9 carbon chain by numbering from 1, 2, 3, 4, 5, 6, and then up 7, 8, 9. On carbon number 3, in a 9 carbon chain, there is an alcohol group. 3, nonane-ol, O-L. The prefix for 9, N-O-N-A-N, nonane, and then the ending has changed to O-L to indicate it's got an alcohol at carbon 3. The next process is you located any substituents and numbered them. You noticed at carbon 4, you had 2 chlorines, so you'll hear that as 4,4 dichloro. And at carbon 6, you had a 2 carbon chain that is called ethyl. So at carbon 4, 2 chlorines, and at carbon 6, an ethyl. And did you locate any of those chiral carbons? We have to give those the R or the S designation. All right, I've just resumed recording. I had to take a quick break there and let the dog out, so thank you for your patience. We were working through this problem here, and we're just kind of recognizing that this particular molecule had 2 chiral centers, and therefore labeling those in their configuration of both spinning clockwise. Just recall, if that needs a little bit of review, here is the first priority at the O. The second priority would be the carbon leading to other interesting positions, such as the chlorine. Carbon number 3 heading left, the ethyl group, would be the third priority. And of course, the hydrogen, which is the 4th priority. Connecting these dots actually makes it spin counterclockwise, but we know to flip to the clockwise position since the hydrogen is coming out of the page, and it ends up to be an R configuration. Same idea here. This is a chiral center. Notice that it is a carbon leading to 3 other carbons, so you're trying to find the first point of difference. The 4th would be the hydrogen, which would be of lowest priority. Here we have a carbon with a 2 carbon member chain. Here is a carbon leading to interesting chlorine, and this is a 3 carbon chain. So thinking that through, the highest priority would be the carbon chain leading to the halogens. The next priority would be the carbons that have 3 in them. Finally, the carbon branch with just 2 carbons. And that's why it's spinning R, it's spinning clockwise. So putting that all together, what did you come up with for a name? At position 3, there is an R configuration, as well as position 6, there is an R configuration for chirality. Dash 4,4 dichloro, that's alphabetical for chlorine. Dash 6 ethyl, 3 nonane ol, the OL ending for the alcohol. How'd you do? Would you like to try another? If so, write this molecule on your paper. This is one from your homework. Give it a whirl, remembering what we just talked about. If the alcohol is directly off of a benzene, it has a different last name. Pause the video and work this one out, and when ready, come on back. All right, so you're back. You must be ready to check your work. Let's go through this example, and you recognize that when that OH is attached to the benzene, that it has a new parent name. It's called phenol. Remember, this is carbon 1, and I have to number around to give the rest of those a substituent number. So at carbon 1, we do not need to label that. You already know that OH is at carbon 1. But I have two groups of ethyls coming off of position 2 and position 6. So this is simply named 2,6 diethyl phenol. How'd you do? Let's talk a bit about physical properties of alcohols and just comparison of their boiling points from a straight chain ethane to a halogen chloroethane and finally to an alcohol called ethanol. You notice that as we start adding interesting functional groups, we create stronger and stronger intermolecular forces, and we'll notice that the boiling point will reflect increased molecular attractions. Notice that in ethane, which is just a non-polar molecule, there is no functional groups, so the only type of intermolecular attractions they would have are those temporarily induced poles known as dispersion forces or London dispersion forces. With the chloroethane, we introduced a polar region to the molecule, a little more interesting, where the electron density is rich around the chlorine, and therefore not only do we have dispersion forces, we've also have the dipole-dipole force, a stronger intermolecular attraction based on the polarity of the molecule. And finally, when we introduce the alcohol functional group, we meet the criteria for dispersion. All molecules will have dispersion forces. It is also a polar molecule, so we have dipole-dipole. But now finally we meet the criteria for the strongest intermolecular attraction of all, the hydrogen bond. So ethanol molecules, or alcohols in general, will have the highest intermolecular attractions possible, very sticky molecules. They adhere well to one another. And it takes a whole lot of energy to overcome that stickiness, that intermolecular attractions due to H bonding, where the oxygen on one alcohol is highly attracted to the hydrogen on the second alcohol, creating up these very strong hydrogen bonds, giving them an extremely high boiling point in comparison to other carbon molecules of equal molar mass. Let's kind of show that. I'm going to back that slide up just quickly again and just show that solubility trend as well. And this is an important second physical property we should discuss. The solubility really is related to the number of carbons in the chain of the alcohol. If you have a very short carbon chain, you will see that the hydrophobic region, which is the non-polar region, is quite short, and therefore the hydrophilic region, which is the polar region, will very much interact with the polar water molecule. Remember the solubility rule, likes dissolve likes. And if I have polar, it will dissolve other polar molecule. With a short carbon chain on the alcohol, the hydrophilic region dominates, and we can have solubility. One liquid dissolve and another is truly a miscible liquid. But as we begin lengthening the carbon chains, this non-polar region, the hydrophobic region, dominates, And the hydrophilic region is quite small in comparison, and so this ends up to be non-soluble in water because now the nonpolar region is interacting and it's not really allowing the hydrophilic region to participate in solubility. And I've noticed about 6 carbons is the trend. 6 carbons gives you too much hydrophobic region, and the alcohol becomes insoluble in water. I know that you did a lab where you were using a 6 carbon chain, 1, 2, 3, 4, 5, 6, and a primary alcohol at the end. This would be 1-hexane-ol, and this was insoluble in water. Our next section talks about the acidity of alcohols, and it comes back to us from chapter 3 when we first learned about acid-base chemistry and the pKa chart. So this will be a little bit of review from that section, just bringing it back to our forefront. So remember, the acidity of a compound can be qualitatively evaluated by looking at the stability of its conjugate base. So here is the hydrogen that's attached to the oxygen on an alcohol. So this is the hydrogen that we're looking to deprotonate, to remove the proton to create a deprotonated alcohol. The name of the deprotonated alcohol is called an alkoxide ion. So for instance, if we had methanol, which would have 1 carbon, that's the term for 1 carbon alcohol is methane-ol. And we deprotonate, if we remove that hydrogen ion, we end up with a methoxide, there I could draw it this way, a methoxide ion. And it's going to carry a negative charge because we've removed the proton. These two are known as conjugates. This is the conjugate base. This would be the acid. They are distinguished by the removal or gain of just a single proton. So as we think about the ability to stabilize the negative charge, we can relate the following trend. That negative charge on oxygen, it is more stable than a carbon or a nitrogen, and that's just the periodic trend. Remember in the row, it goes carbon, then nitrogen, then oxygen, then fluorine. So the increased stability in that same row on the periodic table, period 2. So oxygen is more stable than a nitrogen, which is more stable than a carbon. But still, as I move down the chart, I can find more stable with halogens. So coming down in period 7, when you have chlorine, bromine, iodine, and so forth, this is the increased stability. So kind of thinking about the stability of the negative charge on the conjugate base is giving us an idea of how strong the acid is. How easy is it to deprotonate this hydrogen? So it's easier to deprotonate an alcohol than it would be an amine, and certainly it's very difficult to take a hydrogen off of a carbon. That's a very nonpolar bond, so it's very equal in electron distribution. The nitrogen, a little bit easier to remove a proton, but more likely they want to receive a proton. And then here, of course, the alkoxide anion, but the most stable would be, for example, your chloride, your bromide, your iodide in terms of their acidity. So that means that HCl, HBr, HI are stronger acids than we would have for an alcohol. But an alcohol is more acidic than an amine or a carbon. So the essential question to ask yourself is, based on the stability of the negative anion, its conjugate base, we can look at the pKa's for the alcohols in the range between an amine and a dihalide, looking at like an HX or HBr or so forth. So they lie between about 15 to 18 is what we saw on our pKa chart. So alkanes, amines, alcohols, and hydrogen halides are in this progressive order in increasing of acidity. And all you're really asking yourself, the stronger the acid is over here, the easier it is to remove the proton. the stability of the conjugate base to stabilize that negative charge determines the strength of that acid. When we look to deprotonate, there are a few reagents that we can use to deprotonate the alcohol, and there's two most common ways that we can achieve that, and we'll talk the first and then we'll look at the second. It's going to take a very strong base to deprotonate the hydrogen from an alcohol. The hydride ion, which is H negative, the hydride ion meets that criteria to deprotonate a hydrogen from an alcohol. Here's an example. I have a 2-carbon chain, 2 carbons, so that's ethane, and it's got the hydroxyl group, so it's ethanol. Notice we do not need a 1 in front of that. With a 2-carbon chain, we know it's at carbon 1 because we simply have reversed the molecule if it's on the other side. So no need to label that with a 1, it's just known. So that's simply called ethanol. We see that it has an acidic hydrogen. Any hydrogen that's attached to an oxygen is considered to be an acidic. And we take a very strong base and it just reaches out and there's a new bond that forms, collapsing that bond onto the oxygen. So the collapsed bond now appears as a set of dots, making it a negative, which would be the ethoxide anion. Notice the spectator sodium migrates over to just keep it electrically balanced. And now what's formed is molecular hydrogen. You will actually just start to see bubbles come out of solution as the hydrogen bubbles evolve. So as they come out of solution, you'll see bubbling here. Ethanol can be deprotonated with a strong base such as hydride, generating hydrogen gas and the ethoxide ion. There's a second way, which is actually probably an even easier way to generate the conjugate base of the alcohol acid, and that's by using any active metal from group 1A. Lithium, sodium, potassium are all very active metals. And when you look at the deprotonation here, again, the elemental form is just removing this one lone electron here is going to kick out the hydrogen, and what you'll have there is a half a mole of H2, that's just to keep it balanced, giving a conjugate base of O negative, which is ethoxide. The sodium ion then migrates over to keep it a positive charge. So the electron, the lone electron of sodium is taken and thus remains as an Na+1. The hydrogen gas would still bubble in solution. Notice how they really balance this is saying 1/2 of H2 is 1 hydrogen. If you wanted a full mole of hydrogen to just balance, you would need 2 moles of sodium to do so. Okay. So that's just keeping the equation balanced. The big picture is saying we can use a strong base, such as hydride. We accomplish the same thing. Bubbles of hydrogen come out and we've produced the sodium ethoxide. Or we can use an active metal, such as lithium, sodium, potassium from group 1A. We accomplish the same task. The ethoxide ion is formed and you'll see hydrogen bubbles come out of solution. We're asked to just simply practice, draw the alkoxide ion that is formed. And it really is that simple. When you get to this problem on your homework, it's just like automatic pilot. The H gets deprotonated and you form the negative ion. I don't care if elemental sodium is sitting on the arrow. It could be potassium, sodium, lithium. Any first family metal will accomplish the same thing. We'll have our cyclohexane and the O negative, which would be a cyclohexane oxide. The anion has formed. And even though we're not asked, just to keep in mind, there would be 1/2 a mole of gaseous hydrogen coming out of solution to keep the equation balanced. Here we have a hydride, which is a negative ion, a strong base, just to keep us in mind. There's a sodium didn't disappear. It's just now a spectator ion, and it's present to keep the solution electrically balanced. Here we have a 1, 2, 3, 4. So this going the other direction. 1, 2, 3, 4. So here we have 2 butanol. Here we'd have cyclohexane ol. No number 1 needed. At carbon number 2, the OH simply changes to an oxide anion. This would generate a full mole of hydrogen gas. So anytime you see that hydride or an active metal, you just simply deprotonate the alcohol to form the anion, which is now ready to move into a next step in your synthesis strategy. Every one of those in the homework problem will follow this trend. There are no tricks with this problem. When we look at factors that affect the acidity of alcohols, there are 3 factors that we'll talk about. The first of those 3 factors is resonance. Resonance of phenols make this millions of times more acidic just simply because it is resonance stabilized. So look at the difference here. This is a cyclohexane ol, all single bonds. So when I deprotonate this and I come up with its conjugate base, there is only one place where that extra electrons can be stabilized, and that's just directly on the oxygen atom. However, when I deprotonate phenol and form its oxide, notice that there's an ability to move those electrons around using arrows to help create stable configurations through resonance. And that's what we've located here. The removal of your proton created an oxide ion. That negative charge is directly adjacent to a pi bond, and so we can see a shift. The extra electrons can be moved to create a double bond. The double bond moves to create a pair of electrons, and that's where you see the negative formal charge appear. And look what happens as you progress through all possible resonance structures. You'll see that from the start, and this is the same structure here finally at the end, there were 1, 2, 3, 4 unique resonance structures. So as a result, the hydrogen on the phenol, because it is resonance stabilized, is extremely acidic. It's much easier to remove than you would have for the cyclohexanol. Remember the definition of a strong acid. The easier this is to remove is based on the stability of its conjugate base. Since this is much more stable because it can be stabilized through resonance, this is a stronger acid than the cyclohexanol because this is not a very stabilized conjugate base. So therefore, since it's easier to remove, we really don't need that strong of a base. We can use something like a sodium hydroxide. Hydride, or an element such as sodium, potassium, or lithium, those first family metals, they must be used on an alcohol that has an ane-ol ending. They need a strong enough base to remove the proton. But if I see that it is stabilized by resonance, which means that this alk oxide negative ion is next to a pi bond, we've created a stronger acid because of the stability of its conjugate base being stabilized by resonance. So we don't need as strong of a base. An OH negative is enough of a base to go ahead and deprotonate phenol. Okay, so resonance increases the acidity. The second would be induction. Now, induction says if you have a set of electron withdrawing groups next to the alcohol functional group, you've increased the acidity of that alcohol. For example, in this particular molecule, we have a straight chain carbon. The polarity says this is an electron-rich area, but there's, this is the partially negative versus partially positive region. But what happens when I place a whole bunch of chlorines on carbon number 1 is the electrons become more and more pulled towards the carbon. And if the electron density is being pulled away, that's what induction is, this hydrogen is not held as tightly by the oxygen and is easier to remove. The electron density being pulled away from the oxygen makes this hydrogen easier to cleave. This is a more acidic hydrogen because the negative charge from the conjugate base is very readily stabilized by those electron withdrawing groups. And the third is solvation effects. Solvation effects, in other words, when we add a solvent, can it help to stabilize the negative ion? And I found a picture from your text that helps to visualize solvation. Now, solvation is just really the ability of the solvent to move around the actual anion to help create stability. If I have a straight chain, ethoxide is just simply 2 carbons, and we can see where the electron-rich area is on the oxygen, our solvent has the ability to place itself around that negative region to help create a stabilization force, interactions here, to help stabilize the negative charge. If you compare that to a big bulky base, such as tert butoxide, notice here that you have a very large nonpolar region, and this oxygen is being shielded by the big bulky carbon chain. Therefore, the interactions with that solvent are limited just based on steric hindrance. So the tert butoxide is less stabilized by the solvent interactions simply because it's limited to the amount of space it can create interactions with the oxygen. So you'll see a straight chain carbon is more acidic, easier to remove the hydrogen because I can stabilize this charge with the solvent interactions. And if I have a big bulky base, it is less acidic because the negative ion is less stabilized by the solvent interactions. So in this section, we simply reviewed how is the acidity of an alcohol affected by resonance, makes it more acidic if it can be stabilized by resonance. By induction, it makes it more acidic if it can be stabilized by electron withdrawing groups. And the third, the solvation. You are more acidic if the solvent can stabilize the negative charge by interacting around a larger surface area. Those are the 3 conditions that affect how easy it is to remove the hydrogen by stabilizing the conjugate base. Let's practice. In this particular example, we're asked to identify, and this is a series of questions on your homework, and I just took a snapshot of one. Identify which of the following compounds is expected to be more acidic. Which one would you choose and why? Well, I hope you notice in compound A, we have a double bond. And the double bond simply tells me, it's the only difference between compound A and B is the presence of a pi bond. 1, 2, 3, 4, 5. So between carbon 2 and carbon 3, you see a pi bond. And that tells us that it has the ability to be resonance stabilized. Even though, like in compound A, if I were to redraw and show the formation of the alkoxide ion, I have a ketone functional group at carbon 4. This alkoxide ion has the ability to be resonance stabilized. So that tells me that a pair of electrons can collapse in and form a pi bond. And when it does so, it has a resonance structure. The pi bond that's originally here will move its electrons to create a new negative charge on carbon number 3 or carbon number 1. is going to move between to form the most stable configuration. So here we now have a pi bond and the new set of dots at carbon 3. And we can continue moving those arrows. We're just recognizing that as soon as we have a pi bond next to the negative alkoxide oxygen, we have resonance stability. This particular bond is not near a pi bond, even though there's one in the molecule. It's not right next door, so this is not resonance stabilized. So we've decided, just based on the ability of resonance stabilization, the conjugate base of a resonance stabilized alcohol creates a more stable configuration, and we were able to determine that compound A is more acidic just based on the negative charge being able to be distributed through a series of electron arrow movements of resonance. We started with our first structure, developed the second structure, moved these pair of electrons here, and then finally these pair of electrons can form here, and you see the third resonance structure where the negative charge is now what was originally on the ketone actually migrated up here, and the new set of electrons then, even though they're not drawn, we know they're there. So we had 3 unique resonance structures by a resonance stabilized conjugate base. In the last section of our first video, we begin with a review of how to prepare alcohols via substitution or addition. With substitution or addition, this is the same set of reagents that were in our toolbox from chapter 11. We know that alcohols can be synthesized via alkyl halide in a substitution reaction. Let's give an example of how to create an SN1 or SN2 substitution reaction just based on looking at the substrate. If I have a primary alkyl halide reacting with a strong small base, we favor just think of that as OH negative, sodium being the spectator. We favor a bimolecular collision, a backdoor attack. And we have substituted on then a hydroxyl group and giving us the chloride as the leaving group. So the hydroxyl group will attack the electrophilic carbon and the leaving group leaves. And when it does so, it takes its electrons with, forming a Cl negative, and we formed a primary alcohol. If we have a tertiary substrate, this carbon is attached to 3 other carbons, and we have a tertiary alkyl halide. We use a weak nucleophile, such as a water molecule. And recall that this occurs through a unimolecular collision. It's not a collision, a unimolecular reaction mechanism, where step 1 says the leaving group has to leave, and we create a carbon positive ion, carbocation. So that intermediate, and here I'd recognize that there's no possibility for rearrangement because it is already in a tertiary position. But with the SN1 mechanism, we know that possibilities of rearrangements occur. And here we've created a tertiary alkyl halide, and that protonated alcohol then deprotonates to give us HCl. So just reminding us about substitution reactions and how they created an alcohol. And the other came again directly from our last chapter. These are the same tools from our synthesis chapter. Starting with an alkene, we could have an acid catalyzed hydration. Acid catalyzed hydrations are Markovnikov additions, but they have a possibility of a rearrangement. Check out section 9.4 as review. If you want to prevent rearrangements, we know to use oxymercuration. Demercuration gives us Markovnikov addition, but by keeping that stability with the mercury cyclic intermediate, there is never a carbocation intermediate, and therefore eliminates the possibilities of rearrangement. And finally, using the hydroboration followed by oxidation, you get the anti-Markovnikov addition. So here you created a primary alcohol, whereas Markovnikov puts the OH on the most substituted carbon. Anti-Markovnikov puts it on the least substituted carbon. So this section really is coming out and just making us once again review reagents from our toolbox that have already been placed there. No new chemistry, just a reminder of a previous reaction, those tools that come out. Try this one. Identify the reagent that you would use to accomplish the following transformation. And just coming off your synthesis chapter, these tools should be fresh in your mind. Pause the video, give yourself time to think, and come back when ready. Okay, welcome back, and let's see what you have. Noticing that your starting material is a tertiary alkyl chloride. The tertiary alkyl chloride means that that carbon attached to the chlorine is attached to 3 other carbons. And just a moment ago on the previous slide, I showed you this very slide saying we need a weak nucleophile to promote an SN1, the unimolecular substitution, where we can create a tertiary alcohol. Remember, we use a weak nucleophile to avoid elimination, because if I had used a strong nucleophile with a tertiary substrate, we would form the ene in the most substituted position. We want to avoid that, ending up with an alkene. So we use a weak nucleophile to have substitution over elimination. So all you had to place on the arrow to get that correct was a water molecule. Taking off the bromine in an SN1, the leaving group leaves, forms a carbocation. Remember, the carbocation intermediate here would be a tertiary carbocation, so that would not have any type of rearrangements occur. So that's ideal for an SN1 mechanism. You have more practice here. And again, I'm just going to work a couple because your job then is to go through the skill builders. And these are just some examples of the very problems you'll see in your Wiley. How do you turn an ene into an alcohol? Pause the video and give yourself time to think, and come back when you're ready to check. Well, let's see how you did. Your starting material is an alkene. You want to turn it into a tertiary alcohol. So again, this was a slide just a few pages back where we had an ene, and we want it to go to a tertiary, the most substituted. And so the most substituted means that we need a Markovnikov addition. Looking at your beginning and ending structure, a dilute treatment of acid catalyzed hydration, because we really don't need to worry about rearrangements with the mercury workup, because the carb cation that forms here will be on the most substituted position as it is. And so therefore that intermediate, as we add on, it's going to create the most substituted alkene. So in our process here, we don't need to worry about rearrangements because the alcohol is adding on to the position of this tertiary carbon. So that's it. An acid catalyzed hydration produces our alcohol. Rearrangement is not a concern, as the carbocation will be a tertiary position, and therefore we're looking good in terms of one-step conversion with dilute sulfuric acid. And that's the end of lesson 1. Go to work on your Wiley skill builders and come back to lesson 2 when ready.